and each of us had 10 minutes or 5 minutes, something like that, to somehow see each other. Then Beate was one of the persons that I met there. There were other people. Actually, with one of them, I ended up to send a grant application last July, and with Beate we spoke. And when I spoke with her, she said, "Oh, last week I was in Tartu. I didn't see you there." I said, "Great, I haven't seen you there." And then I find out that she is working in different aspects of modeling and how she can somehow use that to predict or help people and governments even to how to somehow mitigate the problems, health problems, different issues of the infectious diseases that is happening and somehow overcome that. And I think the lecture she's going to give to us today is also going to about that. But also another time from the morning we have been chit-chatting with each other, I find out that she has also a very interesting background. From what I understood, she has actually studied food sciences. And she has studied food sciences in University of Bonn in Germany. And in 2013, she has managed to, within just 2 years, to defend her PhD thesis about modeling of bioterrorism, if I am right, in German environment. And from there, in 2013, she has moved to Vienna. And in Vienna, she has been working as a postdoc. And during that time, before she joins the University of Copenhagen in Denmark in 2021, she has also managed to do her habilitation. And 2021, she has joined the University of Copenhagen as associate professor, and September this year, she is destined to become a full professor there. As if we look at it, she has a very speedful progress. She's not only doing a speed dating, but at the same time, speedfully going up through the academic ladder and the work that you have. I'm not going to take more time from you. I think more, when she gives the lectures, hopefully we would have more discussion and we know her better. Please, Beate. Thank you.
Great, thank you for the introduction. I'm happy to be here today with all of you, and I appreciate the opportunity to talk about my research on the topic Advanced Computational Sustainable One Health Modeling Embedded in an Economic Context. Before we delve into the topic, I want to take a moment to introduce myself. I have spent the last 15 years conducting research on epidemiology, which includes development of models to simulate disease spread and finding the best solutions to control diseases from epidemiological and economic point of view for veterinary public health authorities. My work has also contributed to legislations, and I worked on 23 diseases, 11 species in 11 countries, and some of my work has involved analyzing global data. I have been involved in research fundings of more than 23 million euro. In the last 2 years, I have raised funding of 3 million euros, which I'm using to finance my own research group in Copenhagen, which now consists of 8 scientists. Yeah, and in the last 10 years, I have published more than 70 publications, which we can covered in 6 main categories. These 6 main categories are developing of computational modeling frameworks for preparedness and outbreak response, such as for Salmonella Dublin, FMD, BVD, PRS. Also analyzing environmental and climate data, studying surveillance and infection disease data of humans, such as foodborne diseases or contamination of water pans in Africa, evaluating antimicrobial usage and antimicrobial resistance, focusing on animal health economics, and I'm providing data science supports for my colleagues in the area of animal welfare, slaughterhouse, microbiome studies. And the One Health approach requires to link these areas, animal health, human health, environmental health, including treatment, economics, and others, with the aim to sustainable balance and optimize health by considering the sustainable development. And this refers to systemic thinking. It's important that we increase the disease resilience in animal production while contributing to sustainable One Health actions. Therefore, it's important that we move from to react to outbreaks to prevent them. And for this, it's necessary that we consider the interassociations between different system components, how different systems interact with each other. And my recent work illustrated how important it is to build the link to different disciplines and systems. And one example is Salmonella Dublin in Denmark. Salmonella Dublin is endemic in the Danish cattle population and is a zoonotic disease. And humans can become affected via direct contact with cattle, fecal matters, or through consumption of unpasteurized milk or contaminated beef products. And many Salmonella Dublin infected cattle do not show any clinical symptoms, which make it very hard to control Salmonella Dublin. Consequently, the government's implemented an eradication program since 2010. This program includes movement restrictions between Salmonella Dublin infected and non-infected farms for both dairy and non-dairy farms. On top to the movement restrictions, a regionalization was implemented in the period 2013 to 2017. And the regionalization you can see here in this map. The regionalization include movement restrictions between the red highlighted areas, the geographical areas with a high Salmonella Dublin prevalence, and the green geographical areas with a low Salmonella Dublin prevalence. This means that cattle cannot be moved between these both areas, even if the farm located in the red area were Salmonella Dublin free. Despite all efforts made to eradicate Salmonella Dublin in Denmark, the herd prevalence is still on rise. Therefore, we got funding to analyze why is the apparent herd prevalence increasing in Denmark despite movement restrictions between Salmonella Dublin infected and non-infected farms. And we should gain new knowledge regarding the transmission pathways and quantify the associated impact of the pathways for Salmonella Dublin spread. To address this question, we have merged the cattle movement database with the surveillance diagnostic database for Salmonella Dublin over an 11-year study period. Here you can see just 1 month of the merged data. The red lines shows the movements between infected farms, and the green lines movements of non-infected farms. And the thickness of the lines represents the number of moved cattle in this month. In addition to investigating whether movement could be a transmission pathway, we also looked into the possibility if local transmission could be another transmission pathway. So we searched for infected farms within a 5-kilometer radius and analyzed if new infections occurred in the same area in the next 1, 2, 3, 4 months. And we identified that the strongest predicted factor to become Salmonella Dublin was through movement activities between cattle farms, with twice the odds ratio compared to the local transmission. The odds ratio to become infected via movements decline over a prediction time window of 6 months, while the odds ratio for local transmission stay constant over the study period. Our model also considers the fact that fewer farms exist in Denmark, but the farm size increase, as the model was adjusted for farm size, trade months, production categories, and so on. After identifying that the cattle movements play a crucial role in the transmission of Salmonella Dublin, more so than the local transmission, we decided to perform a more comprehensive study on the cattle movements by stratifying the cattle movements between infected and non-infected farms. And based on the network analysis, the trade patterns of infected farms were not changed due to movement restriction, including the regionalization. The regionalization is shown here with the pink lines from 2013 to 2017, and we couldn't find really a difference before or after the regionalization. Although we identified clusters, so farms that trade more with each other compared to the rest of the network, we identified a high inloyalty of the Danish cattle farms. Only 2% of the business relationship from 2010 still existed in 2020, causing shifts in the cluster all the time over the study period, which make it quite difficult to use clusters to enhance surveillance for veterinary authorities. Therefore, due to the switch of the clusters, because some farms disappear over the study period, it's quite difficult to use our results to improve the surveillance in Denmark. Although we couldn't find effect of the movement restrictions, including the regionalization on the trade behavior of infected farms, and we couldn't find useful clusters for the veterinary authorities, we still didn't want to give up. Therefore, we performed a more detailed analysis by focusing on these blue-colored farms here. This blue-colored farm has a high betweenness. This means this farm connects many sub-networks. And farms with a high betweenness might seem unimportant in a trade network, as they have only few direct trade partners, colored here in pink. But if an infection occurs in the blue-colored farm, then the pathogens can spread only with few movements to many other farms. And our question was, what would happen when we remove these farms with a high betweenness from the trade network? How does influence the spread of Salmonella Dublin compared to remove of random farms? And for this purpose, we developed a simulation model that simulates the spread of Salmonella Dublin on cattle movements. And it's a stochastic, susceptible, infected, recover compartment model. And we simulate the spread on the actual observed trade activities of farms and by a range of hypothetical movement activities by decreasing and increasing movement activities in order to analyze how change in the movement activities would influence the spread. And the model should provide us information about the outbreak size, so how many farms can become affected, and the outbreak probability. We also include information in the model what would happen when we targetly remove farms or randomly remove farms. And the outcome of the simulation model was that target removal of 1% of the farms with the highest betweenness would achieve an 88% reduction in the spread of Salmonella Dublin compared to removal of random cattle farms. You can see in this figure the orange line, this is the observed trade activities, and here we decline and increase the movement activities, and here you can see the outbreak size, and what you can see actually that around the observed trade activities we observe the highest outbreak size, so it doesn't make sense to increase more the movement activities because it wouldn't reach more farms. We are actually at the threshold. We never found the situation in the model that all farms become infected, although we increase the movement activities. And the outbreak size of 85% infected farms suits quite well the observed number of newly infected farms in Denmark. But I have to say, this only appears in a model with a very high transmission probability. And the main conclusion of our work for the veterinary authorities was that the Danish farmer move cattle much more than other European farmers. For instance, the Danish farmer trades 10 times more than the Slovenian cattle farmers. We identified similar network trends for infected and non-infected farms despite movement restrictions. And the rare long-range animal movements on average a cattle was traded 70 kilometers, favor the resilience against spreading of Salmonella Dublin to other regions. probably causing a higher prevalence in already high geographical areas in Denmark. So we increase more the prevalence in already high prevalence area. Therefore, the regionalization based on these model results doesn't make sense. Doesn't make sense because the movement activities happen in a long range distance. And one of our recommendations was to understand why farmers trade infected cattle and encourage them to follow the Danish legislation. And after preparing some research and talking with farmers, we figure out the farmers have the possibility to establish multi-site businesses. Multi-site businesses consist of farmers that belongs to the same owner, colored here in green, on another owner. If one of these farms become infected in these multi-site businesses, automatically all other farms became also infected, even if there is no transmission of Salmonella Dublin via movements. What is the reason of the even increasing number of multi-site businesses in Denmark? This is our economy. Our Danish tax system favors the establishing of more and more multi-site businesses. What is the consequence for my research area? I find a higher proportion of false positive test results in the surveillance program because I see they are infected, but maybe they are not infected because they were never tested. They are automatically become infected because they are part of the multi-site business. Consequently, my former research overestimated the impact of movement activities as a transmission pathway. And also our increasing number of biogas facilities can be another reason why Salmonella Dublin can spread, because transportation vehicles collect the manure from farms and bring it to the biogas facilities. With this example, I wanted to illustrate that it's important to understand the surrounding systems, our economy, our tax system, our energy sector. So make sure for your research to have to look on the right and the left side when you prepare your research. Show the willingness to understand other surrounding systems. It's okay to be an expert in your system like animal production, but show the willingness what can influence my system as well in order to avoid the situations that you try to improve the system on one place, like use manure for our biogas, but make it worse on another place, for example, spreading of Salmonella Dublin. And it's often the case that our economy drives us to grow, compels us to increase the farm size, resulting in more transmission pathways as more animals are present in the herd. Every year, 3 new agents jump from animals to humans, causing a potential zoonotic or pandemic risk. To address this, we invest in control programs, developing new vaccines, antimicrobials, and this results in antimicrobial resistance and causing public risk and a lack of trust in our animal production, leading to economic instability, which used to be our primary driver of growth. Climate influences animal health, such as heat stress, can reduce the milk production, but the animal production contribute with 40% of the global greenhouse gas emissions. And animals produce 4 times more feces, and methane and nitrous oxide from manure contribute to the global warming. We feed our animals with crops that can be used for human nutrition, in total 46%. And every minute we deforest the area of equivalent of 7 football fields for animal production. And with our behavior, we increase the climate impact as we destroy plants that have the possibility to transform CO2 to O2, but there are fewer and fewer of them. Again, we're contributing to global warming. And each temperature change moves ecological zones on Earth. Some species will survive, and some species may have to move northwards to find suitable land cover habitats. And actually, we are losing 3 species per hour with cascading effects on our ecosystem, food chain, and health due to infection. And we have to notice these interassociations, the interconnectiveness of system components. Otherwise, we will try to improve one system and make it worse on another place. And this is complex and a big issue, but it doesn't have to be so complex to notice interassociations. For example, when we consider diseases, often diseases are interconnected, merged with each other. For example, when you have a look here on the figure, paratuberculosis is often associated with lameness or with clinical mastitis. Lameness is associated with milk fever, mitриtis, and a bunch of other diseases. And it's important that we consider these interassociations, otherwise we overestimate the effects all the time. And my team in Copenhagen is working on an approach where we would like to assign association more to one disease compared to other disease. And this is the modeling framework where we were working on, and it should maybe become available as an R package in the future. And this helps you to identify these interassociations and deconflate and de-nested the associations. And this is based on Bayes' theorem. Bayes' theorem helps us figure out how likely event A is given that event B happened. So how likely is that when lameness exists, that paratuberculosis exists as well. And we're working on this tool that should help you to deconflate and re-nest the association. And our plan is that you can upload different kind of data sets based which data are available in your field studies. And we applied this modeling framework in collaboration with the VOA Center of Burden of Animal Diseases for global dairy cattle diseases, where we consider the association, for example, of clinical mastitis, and we deconflate the impact and express it as production losses in US dollar. And you can see when we consider the interassociation of clinical mastitis with many diseases, the production losses are much lower compared to the scenario where we just neglected it. And this modeling framework we would like to expand to other system components, and I think the next step would be the mitigation measures. Because I'm convinced that only a combination of several mitigation measures will help us to make our production more disease resilient. For example, via genetic selection and breeding programs, we can make our animals less susceptible to specific pathogens, like by 10%, with feed additives, biosecurity, new vaccines, and herd management. And I think it will be a puzzle of many different mitigation measures in order to increase the disease resilience of animal production. But studying the epidemiology is essential for any system to become disease resilient. We cannot implement mitigation measures with the purpose to reduce the prevalence without knowing how this influences the disease dynamic. Therefore, my conclusion is that we need the epidemiology to analyze to what extent we can make our animal production more disease resilient. We can't live without epidemiology. It's nice to have a modeling framework that helps you to analyze such associations, but of course we need data. And especially we require data like environmental data, bioclimate data, and we have to analyze how this impacts our health. And we study the mosquito population of 20 years, where we use the evidence of mosquitoes from US and also climate data. And we have demonstrated that it's very important to have monitoring programs in place because when you consider different stages of a mosquito from egg to adults, by using these empirical long-term data, then you get other predictions compared when you use literature data. And long-term monitoring are therefore essential, in particular to those of systems related to our health and heavily depending on climate. On top to the modeling framework and data, we need also an exchange of data from the animal sector, human sector, and environmental sector. But in order to exchange data and combine different data sets together, we need a secure data flow. And my colleague developed an approach where only authorized people can read and work and use data. For example, when I lose my hard disk and you find my hard disk and you would like to work with my data on my hard disk, then you can just see randomly numbers. You can't work with this data. And this is a secure data workflow which we have established to build trust between the institutions that deliver or provide us with data. It's better to have this established procedure instead to say, after losing my hard disk, sorry, I don't know who has the data and I don't know what will happen now with the data. But I think we need much more to establish sustainable One Health actions. I think we need human creativity for sustainable One Health actions. We can't do the same experiments which we did the last 50 years. And one example is here from University of Copenhagen, from a colleague of mine, the project called Plastic Cow for Circular Economy. So he take advantage of the natural enzyme capabilities of microbes found in the pre-stomach of cows, and he used these to degrade common plastics into the commercial components. This is one example how our sector can be used for sustainable actions. But I will go further. I think we have set up a completely new field in experimental studies in order to move from association to causal discovery. Often, and I'm doing the same, when I perform my studies, I always adjust to confounding variables. When I compare case control, I adjust to breed, farm size, sex of the animals, etc., in order to get nice, significant values, right? But we live in such a complex world, we can never include all confounding variables that influence our studies. And therefore the question, let us implement studies that are heterogeneous. For example, when you introduce a vaccine campaign in country A and B, and you would like to analyze the association between vaccines and immunity, do it for the total population and see if you find an association. Maybe you will not find an association, but this is also a result. Instead, always to adjust our results to get nice values. But again, I will get further. I think we have to rethink our economy. And it's called, the donut economic, because the donut economic say the economic growth should be our second priority. Our priority should be to live inside the donut, so put the biodiversity, the climate, sustainability in the front. This should be our priority, that everyone can live on this planet. And the second priority is to grow. And some cities like Amsterdam already introduced the donut economy. Plan is to rebuild the cities by using the resources in a sustainable way while fulfilling the citizens' needs. And some countries perform better than others with the donut economy. Here's an example. You see here 2 different periods, Denmark, Costa Rica, and Estonia. The circle here is how well we live in our country. This is our environmental impact and the use of our resources. And some countries like Costa Rica, they perform better. They are better in conservation of the biodiversity, using the nature, and can live quite well compared to other countries, for example, like Denmark or Estonia. And one example of a project where different countries work with each other, exchange data, is a project with the EUFMDIS, the European Commission for Food and Mouth Disease, where different countries are sharing the data where it's possible to analyze transboundary spread. The countries provide data regarding the movement, the resources, how many vets we have for outbreak response, etc. And then every country can analyze their outbreak, for example, for FMD. Where are the bottlenecks? If I miss, for example, surveillance teams or culling teams, which mitigation strategy is the best to bring FMD under control? And the model is implemented in 14 countries, and also Estonia is included. And with such a project, we can create European solutions or find European solutions and work together, for example, on transboundary diseases. And last month, we established a Center of Excellence for Disease Modeling. And the model is not just for FMD, it will be expanded to Rift Valley fever, sheep and goat pox, lumpy skin disease, and others. And when we have a common tool then established in Europe, then we can figure out that we will not find a common solution for Europe. It can be for some system components where we find a common solution, but we have to consider that each country has their own circumstances. For example, when we apply this model and for FMD and want to figure out what are the most efficient and effective mitigation measures for Austria and Denmark in case of an FMD outbreak, then for some scenarios in Austria, the vaccination would be the most optimal mitigation measure. For Denmark, it's the basic mitigation measures like standstill period of 3 days, culling of the animals. So be aware that the solution can differ between countries. But we can just figure out that the solutions will be different when we have a common established tool. And my preference is always to have a tool at the EU level. The conclusion is we have to consider that our animal production, our system is closely linked to many other systems, and they influence us, we influence them. We have to identify these associations, what are the impact of our actions. We need new study designs, new methods for causal discovery. At the moment, we can measure associations. But we need also in the future, I think, to produce more efficiently using fewer resources. As I show you, we can't continue like we continue now, while also increasing disease resilience. For this, we need nature and technical new solutions to be creative and change our behavior, for example, regarding the donut economy. But in particular, we need intra and interdisciplinary collaborations. And these are some of my collaborations, but I think we need very strong leadership and actors with the right attitudes working together who can bring the different disciplines together to work on one common aim. And if we reach this, if we work together and understand each other's systems, I think we will be successful in preventing more infection diseases, contributing to sustainable actions, and tackling One Health challenges. Because under the motto, what is good for the world will be good for us. And that's it.
Thank you very much, Beate. It's open for discussion. You have any questions? And Rosa can come and give you the... Shall I ask the first question? In the first part that you were speaking about the modeling that we did for the movement of Salmonella, you noticed that there were betweeners, that you were somehow showing that they are having a lot of influence in the spread of the disease.
Mm-hmm.
And if you have taken them out, you would be nearly taking 80%. You don't
yeah.
of the disease.
Yeah.
And so, but why? I mean, why those betweeners are even there? There should be a reason that that glue is there. How you want to tackle to just take that out? If you look at that, there is a reason that you have that betweeners, that they are somehow spreading there. And I fully agree with you. You have to have a complete multi-dimensional way of thinking, from the tax to investment and so on. But, okay, they are there, but what is the solution? How you want to take them out of the system?
Yeah, in my model, I remove them, but I think we can, for example, increase the biosecurity in the real world instead to remove farms from the system, implement other treatments in order to reduce the risk of spread of the pathogens of the farms with the high betweeners. Because I just wanted to illustrate that we have farms in the systems who can be a spreader, right, a hub, and therefore we have to be careful. In my model I remove them, but I think in reality we can use non-drastic measures like implement biosecurity or isolate them or something like this.
Any questions?
Thanks for your speech, Professor Conrady. How strong may be contribute the early diagnosis in the disease for the One Health approach? If you talk about some examples.
The diagnostic?
The early diagnosis.
The diagnosis.
Oh, early diagnosis. Or non-invasive diagnosis of diseases for
Salmonella Dublin?
Yeah.
This is one issue which we have, because the diagnostic is not perfect. So I think the sensitivity and specificity is around between 85 and 90%. So we have issues with the diagnostic, but I think one issue is that it really differs per herd, because when we consider the optical density value of the bulk tank milk, then several herds have very low, and then from one month to another it goes up. And other, it's really nice that you see a slow increase, so it's really hard, it differs, and I think the herd size is one of the main issues in Denmark, which influence, of course, the early detection, because it differs per farm, because the herd size are so different in Denmark. And yeah, of course we can improve the diagnostic, but I think it's not just the diagnostic. I think we have to consider the drivers, because we see a high increase in the prevalence in the summer period. The bacteria survive better in the environment because the temperature is good. We have to consider several factors, not just movement and diagnostic. It's a bunch of many factors in order to create a, let us say, early warning system. But I think one aspect is also what I mentioned, the multi-site businesses that we analyze, that make it sense that we include such system and influence our official surveillance programs that have a high proportion of false positive test results. So I think when we work better together, like so, I don't know, the tech system and the epidemiology system, then we can find a better solution. But I was quite surprised, and at the end I figured out this multi-site businesses. This was surprising for me, yeah. But I think when we combine the drivers, the different systems, and show the willingness to work together, also share data, this is one issue, then I think we will go more in the direction of an early warning system. But at the moment, we are far away from this.
Thanks.
Yeah, I have one other question also. You showed how we are somehow changing, especially in Costa Rica, for example. They have a much better sustained situation compared to what is in Estonia and even in Denmark and so on.
Yeah.
But I can imagine Estonia, particularly in the last 10, 15 years, has had a very high rate of growth, and even the GDP, all the things has gone. And I imagine this is the situation Costa Rica is maybe not one of those evolving economies in the world, but in those that are evolving and have high growth rate, this is something that is happening. What is the solution then to sustain the growth at the same time to be able to not deplete all the resources that you have? Is there you don't want to say to the people not to leave,
Yeah, but you can see here in Costa Rica, so in the circle here, you see how the human well-being, right? That they can live quite well in Costa Rica, but they're not using so much resources. And we in Denmark live also quite well, much better than Costa Rica, because you see the white colors here. But I think compared to the resources which we use and the nitrous oxide which we put in our environment is much higher in our industrial countries compared to countries with a completely different culture. They live in a culture where they care about the nature, where they conserve the biodiversity better than we are doing. And I think we can learn from such countries in the future, because it's clear we can't live like we live now. Yes, in a sustainable way. We will not survive, I think. Yeah. And actually you can have here the link, so you can look also for other countries and also how the calculation is made. It's a nice web page where you can find all the informations, and it's updated for different years. So when you're curious, yeah, I encourage you to use the link, and maybe I can also share my slides. It's not necessary now to write it down.
That would be great.
Yes.
Thank you. Yeah, definitely. Good. If no other questions, we should thank Beate for a very interesting lecture, and wish her well in her adventures, future academic adventures. And today in the afternoon, we are going to be also in Armon's festival. And if any of you